Once the YouTube starts, I will introduce you and close my microphone. Okay, so it is my great pleasure to introduce Jeffrey Adams from the University of Maryland with his talk on what Atlas can do.
Thank you very much for the invitation. It's nice to be able to get out of my house virtually, so somewhere besides teaching for an hour. I'm going to talk about the Atlas Lie groups and representations. This is a large ongoing project to use computers to study representation theory. And there are quite a number of contributors over the years. This is the list of people that have, the main contributors. There have been others too, but the people that have, the primary contributors over the years are here. And everybody deserves credit. This is a large joint project, and I'm not going to be stating theorems with names attributed to them, but it's all the Atlas project. Before I begin, I'd like to say that I want to encourage people to ask questions. I'm really not a fan of this, although it's nice to be able to speak at the Weizmann Institute. I'm not a fan of the Zoom conferences. In particular, the lack of feedback from the audience is I find quite disconcerting. So please feel free to interrupt me. In particular, I don't have any big goal in this talk. I'm not going to be like stating some big theorem and proving, you know, sort of showing you the latest and greatest that we've proved. It's more of a tour of some of the capabilities of Atlas. So if I don't get through everything, that's fine too. So please step in. I just realized I have to. This always happens to me. Give me 1 second. I'm sorry, I made a mistake. I have to fix something. Sorry about that. I'll be with you in 1 second. Let's close this. And all right, let's see if that works. There we go. It's not a terrible mistake, but where's the what I was looking at was the handout version, which I had sent to Dimitri, and I prefer this version. Okay, so the unitary dual, the Atlas project is, as I said, it's a computational project to use computers to study questions in representation theory. And in particular, we're interested in the problem of the unitary dual. And this is a famous problem, which many people have heard about, so I'll just state it rather quickly. The setting is a real reductive group, for example, GLN or the symplectic group or E8. And the problem is to compute the unitary dual, which is to say the equivalence classes of irreducible representations of G on a Hilbert space. And that is to say they preserve a positive definite Hermitian form on the vector space. And this is a famous problem that goes back to the 1920s. It's not known in general. There are many cases which are known. Well, on many is a little bit of an exaggeration. Some cases are known. GLN, for example, is known, but there is no answer in general. And this is one of these problems where the answer is known to be very complicated in many cases. So we certainly don't expect there to be some beautiful short description. And we've decided to look at it using computational methods. In the 1980s, David Vaughan stated the following theorem. For any given group G, there exists a finite algorithm to compute its unitary dual. Now, that's a little bit of an exaggeration in that you won't find this statement stated like this in literature. But if you put all of David's papers together with Harichandra's and Zuckerman's and Schmidt's and think about them for a long time, at the end of the day, you will convince yourself that this is true. But that begs the question, which is, it's nice to know that in principle, there's a finite algorithm to compute something, but is it more than that? Could you, could it actually be implemented? And in other words, well, two things. First of all, can these papers be boiled down to an actual algorithm? Can you make it explicit? And secondly, can that algorithm be implemented on a computer? And I want to emphasize those are two different questions. The most interesting and hardest one is the first one. Once you have an algorithm, you can implement it. Now, there may be questions about size and memory and time and so on, but never mind that. The really hard part is the first step, actually coming up with an algorithm. So this was one of these things that we used to sort of talk about at conferences, like, oh, gee, wouldn't it be neat to have a computer to answer this question? But around 2002, we decided to actually take this question seriously to see if we could undertake this project. So there are many reasons to do this. Of course, there's the question of the unitary dual, but there are many, many other questions in Lie groups and representation theory that we're interested in that we'd like to study. We really would like to provide software for the mathematical community for studying representation theory. I don't need to tell anybody here that representations of real groups is a somewhat technical subject, and it's difficult for, say, a number theorist or a physicist who's not a real expert to have access to some of these things. And just like Mathematica or Sage have provided, or Pari have served this purpose for other things, we'd like to have a specialized tool for representation theory. In some sense, this is the main reason, this is one of the most important reasons to me. This is just sort of a personal thing, which is I only really feel that I understand something if I can implement it on a computer. There are many, many times in my career where I've read a paper and thought I understood it. And then when I went to write software for it, I realized I didn't. And well, there are many times when you read an algorithm in a paper and you read something in a paper and you go to implement it and you find out, well, the paper wasn't quite right or wasn't precise enough. So I think that computers play an important role in mathematics, and it's not just helping us solve problems, it's helping us think about the mathematics. And finally, I want to say this, Na'aseh v'nishma. I really believe this and take it seriously, which is that we experiment with the mathematics and we learn that way. And I can't tell you the number of times that I've written some piece of code and I got some answer which was clearly wrong, and I thought it was wrong, and I showed it to David Vogan and the other members of our team, and they said, no, that's impossible. And then after a day or two, we realized it was right and we learned something new. That's continuous. Okay, so I'm just going to state the main ATLAS result here. I call it the ATLAS algorithm, and it's the following theorem. Suppose I give you an irreducible admissible GK module. So the statement of the unitary dual is in terms of GK modules. Then there's an explicit computable algorithm to compute the signature of the invariant form on the vector space, and therefore determine if the representation is unitary. Okay, now there are a lot of asterisks in this. So first of all, I said, suppose pi is an irreducible admissible GK module. So implicit in that statement is that we have software to implement the Langlands classification, and you can specify a representation in terms of the Langlands classification. And it's not true that every irreducible admissible GK module supports an invariant Hermitian form at all. But if it does, the unitary dual, the question of whether this representation is unitary is whether that unique invariant Hermitian form is positive definite. And well, I'm not going to try and explain the algorithm here. The theorem is that there exists such an algorithm, and we've written it down and implemented it in the Atlas software.
And Jeffrey, computing whether such form exists is also possible.
Yeah, so the condition that the form exists is elementary. That there was work of Zuckerman and Knapp in the 70s, which so that step is not hard. Okay, so let me pause here. Oops, now I got to get rid of this. And I'm going to leave that. So here is the web page of the Atlas project. I just want to point it out. It's www.legroups.org. And this is a good reference for everything I'm talking about. In particular, the Atlas software is available there, and you can download it and install it and run it yourself. And I want to point out this section here, the documentation section. There's a whole section here about downloading and installing the software. And if you're on a Mac or a PC, I strongly recommend using Docker, which is explained in these notes. And anyway, and then there's a little bit, well, quite a bit here to get you started using the software. Now, as I said, our goal, one of our main goals, is to make software that's very easy use, widely available and easy to use for mathematicians. I'm the first to say that we're not there yet, and it's not so easy to get started to install and use the software. But hopefully, using this, if you're interested, you can at least get the software running. And feel free to write to me and ask me for help if you have trouble on any step of this process. Okay, let me pause there. Questions? All right. Okay, so today, rather than trying to explain the complicated and fascinating and important mathematics that goes into this algorithm, I thought what I would do is instead give a little tour of some of the things that Atlas can do. And part of the point here is that Atlas can do lots of stuff which is useful to people that aren't interested in the unitary dual, but other questions in representation theory and Lie theory. And here's a list of some of the ones I'm going to talk about here. I'm going to start off by talking about unipotent representations, the question of the geometric question of orbits of symmetric subgroups on flag varieties, the partially ordered set of subgroups of a reductive group, and so on. Probably I won't get through all these things typically, but we'll see how far I get. And each one of these is more or less self-contained. So if I don't get through them all, that's okay. And you can read these notes and see what I read more about it. I wanted to start off with a digression though, partly to illustrate the following fact, which it's a little bit of a sort of behind the scenes fact about why we're doing the Atlas project, which is it's incredibly fun. I just can't tell you how great it is to be working on this, and it's a great collaborative project, and it's fascinating, and it's just a lot of fun. And here's an example of that. So here's a little bit of a digression. Suppose you have a real reductive group. There's a natural question: how many representations does the group have having the same infinitesimal character as the trivial representation? This is in some sense of an important class. This is an important class of representations. And by a theorem of Harishchandra, this is a finite set. So whenever I see a finite set, I'd like to know its order. Well, so for example, for the split group of type E8, the answer is 526,471. Now, that was one of the first things we learned when we started writing the Atlas software. We did not know what that number was going to be. In fact, we were expecting it to be more on the order of the Weil group, which is about 700 million. And if it had been that, we would have been in trouble because we need to deal with matrices of this size, and we would have been in a lot of trouble. But it's more like the square root of that. Here's an example for the symplectic group, SP2NR. We just ran the software and computed this for different values of n. So for n is equal to 1, the number is 4, which is to say there are 2 discrete series representations, the trivial representation, and an irreducible principal series. And SP4, there are 18, and so on. So that's kind of nice. And a couple of years, these numbers appeared in a paper. And a couple of years later, I thought, why don't I type these numbers into the online Encyclopedia of integer sequences and see what happens. I got a blank page. That's what happened. Here it is. I typed it in. Whoops. I typed it in here. I typed in the first 4, 18, 88, 460, and I got a hit. And there are the numbers going all the way up to however many. And what is it? Well, it's the number of irreducible representations of the symplectic group with the same infinitesimal character as the trivial representation. Well, talk about a tautology. And this was entered by Sloan himself, N.J.A. Sloan, in April of 2007. Well, apparently he read my paper, but how did he know the rest of these numbers? In fact, he gave an exponential generating function for these numbers right here. Oh, shoot. Right here is an exponential generating function. There are actually several versions of it, but here's one that emerged in 2012. And Sloan did not know how to compute these numbers. I have to think that he had some way of finding the exponential generating function, which computes them. I don't think he had a theorem that these numbers are correct, but anyway, we learned something. So this exponential generating function is the generating function for some combinatorial thing. It has to do with taking n objects and breaking them up into singletons and doubletons and coloring the singletons with 4 colors. I think I got that right. It's something like that. And once we observed that, we could see, oh yeah, that's some combinatorial structure of our algorithm which we hadn't noticed. And this exponential function generating function is in fact correct. So that was quite entertaining. Let me pause. Questions?
Should we make anything of the fact of the date then when this was entered?
April 1st. Oh, you know, I never noticed that before. That's a good question. This final correction here was my birthday, so that's good. Okay, so now I want to briefly talk about
Jeff,
sorry.
Excuse me, can you now provide such a function for other classical groups?
That's an excellent question. For some, yes. So I forget which, I think for orthogonal groups, and for some classical groups, the numbers don't work out so nicely, but you have to group different real forms together in a certain way to get the numbers to work out nicely. But so for example, I think for odd orthogonal groups, certainly for odd orthogonal groups, there's a very similar combinatorial description.
Thank you very much.
Can I ask a question?
Yeah.
For E8, the answer is similar to the answer for SP16?
No, it's much bigger. Oh, that's a good question. Where's SP16? 2, 3.
It's actually
4, 5,
larger for SP16.
Where is SP? Which one's SP16?
Yeah,
56392.
565,392.
Right here.
Can you show the result for E8?
526,000. It's remarkably close.
Remarkably close.
I'm quite surprised that E8 isn't bigger.
2 root lengths makes a big difference. If you compare, if you did SONN, the numbers would be significantly smaller.
So 88.
Sure.
$72,000. Now that's not quite all of them, but it's on that order.
You can also ask for block sizes of SO88, I think.
That's probably what I should have done. So this bottom row, if you add up those numbers, that's the number for SO88. So as David pointed out, it's significantly smaller. Good questions, thank you. Okay, so unipotent representations in Atlas. I'm just going to state a theorem. There's an explicit algorithm to compute unipotent representations. Now there's a number of asterisks in this, in particular, exactly which definition of unipotent representations I'm using. But it would take a whole hour to make that precise, and I don't want to, but anyway, there is such an algorithm. And we've implemented in the Atlas software, and given a group G and a complex nilpotent for the dual group. So unipotent representations, these were conjectured by Jim Arthur, and they're given in terms of some data on the dual group. In particular, part of the data is a complex nilpotent orbit for the dual group. So associated to that is a set of representations which we compute. And I just want to mention some of the things that you need to do it. Well, you need to know about how to compute stuff about unipotent orbits. You need to understand their centralizers. You need to understand the coherent continuation action of the Weil group. You certainly need to know the Cauchy-Linguistic Vogel polynomials. You need to know about cell decomposition of the Grothendieck group. You need to know about special representations in the cells, duality of nilpotent orbits, and the Springer correspondence. So these are all things that we had to implement in the Atlas software in order to do this computation. And here's the answer. So this runs over all the real forms of the exceptional groups, and for each one, the number of unipotent representations. So for example, well, the compact group always has just one, the trivial representation. The split group of type G2 has 12. And the split group of type F4 has 75, and so on. And the total is 1,465. There's a tremendous amount of fascinating mathematics in these tables. The lists, you know, I'll briefly show some of these tables later. All the additional information about these representations that goes into this. This is just kind of the summary. Okay, so what did I want to say next? Oh yeah, let's go back up here. Unitarity. Well, so the Atlas software is all about unitary representations. When I said we've computed these representations, that is to say, we've computed the Langlands parameters of these, so to speak, unipotent representations. To say that they're unitary is an additional statement. And the theorem is that for exceptional groups, they are. Now, for classical groups, it's sort of known, at least in many cases, that they are. But in any event, for exceptional groups, it's a finite problem, and the answer is yes. And here's a sketch of the proof. So this is a joint project between Atlas and Stephen Miller and Joe Hundley. So Miller and Hundley realized many of these unipotent representations as L2 residues of Eisenstein series. So that proves their unitarity. Many unipotent representations are obtained via induction from Levy subgroups. And this gives you an inductive calculation to reduce to smaller groups. After you put those two things together, of those representations I listed, there are about 50 that we couldn't prove were unitary. And well, that didn't follow from the previous two steps. Many of these can be shown by Atlas to be unitary. You just run the Atlas software to compute them, but the remaining 12 are rather difficult. In principle, they could be computed, but it just takes too long or too much memory. By various mathematical tricks and reasoning, we were able to reduce it to 3 representations of E8. And after a lot of work by Mark Van Leeuwen, who is somewhere on this, attending this talk, a lot of work by him to optimize the calculation, we were able to show these last 3 are unitary computationally, and this required about 700 gigabytes of RAM. Before the optimization, we tried running it on as large as 1.4 terabytes and failed. Okay, so now let me put that aside and just talk about some of these calculations that Atlas can do. So here's an example. Suppose G is a connected complex reductive group and P is a parabolic subgroup. Theta is an involutive automorphism of G, and H is the fixed points of an automorphism. It's well known that H acts on the flag variety with finitely many orbits. And whenever you have an algebraic group acting on a projective variety with finitely many orbits, that's a beautiful geometric setup. And it's interesting to study the geometry. So one thing you can ask, the first question is to compute the partially ordered set of orbits, are partial with the closure relations. And this is, well, we do this because this is of tremendous importance in the Atlas software, but this is of independent interest. So I'm just stating it sort of independently here. And just to give people a little bit of warm up, a classical example is you take SL2C and you take the Borel and you take theta to be transpose G inverse. Then H is C cross, and the flag variety is CP1. And this is as Z is acting on the CP1 by multiplication by Z squared. And there are 3 orbits, there are 2 closed orbits, 0 and infinity, and the open orbit, C cross. So the Hasse diagram is 2 closed orbits and 1 open orbit. And the question is, what is this in general? Well, here's the answer for F4. So let me zoom in. Oh, why isn't it zooming? That's too bad. I was able to zoom this, but something about, I can't zoom in. Oh, well, I'm sorry. I can't zoom in, so I'll just have to give you the bird's eye view. So this is the Hasse diagram of the orbits of spin 9 on the flag variety for F4. And up at the top here, although it's just slightly hidden by my bar, is the unique open orbit. And all
actually, if the subgroup were spin 9, the diagram would be a lot smaller. I think this is the SP6 cross SP.
Oh, I'm sorry. It's the split form of F4. You're right. It's C3. Yes, this is the diagram for the split form. And down here at the bottom, there are 12 closed orbits. And in terms of representation theory, that's because, so the way the Langlands classification works is associated to each one of these orbits is a finite set of representations. And associated to each closed orbit is a unique representation, a discrete series. And everything's going on at infinitesimal character rho. This group has 12 discrete series at infinitesimal character rho. And way up here at the other end on this open orbit, there are a number of representations, which are the principal series. Okay. So you can generate these diagrams for any group, and they're a lot of fun to look at. And I should say that these colored lines are giving closure relations, and the color has some additional meaning. There's a combinatorial structure to these sets, which is illustrated by the coloring. Okay, here's another example. It's an interesting question to compute the conjugacy classes of reductive subgroups of G. Everything's complex again. So you have a complex reductive group. What are the conjugacy classes of reductive subgroups? Well, that's a hard question. For example, the conjugacy classes of SL2s is exactly the same thing as classifying the nilpotent orbits. And that's done, but it's hard and complicated, and there's no simple answer. So that suggests that the way I've asked the question is certainly going to be difficult, as stated. So let's look at a special case. Let's just classify the reductive subgroups of the same rank. So they share a Cartan subgroup. This is still a very interesting, rich family of groups. How do you get such a group? Well, an example is the Levy subgroup, which is a centralizer of a torus. There are more general groups. If you take the centralizer of a semi-simple element, you get what we call pseudo-Levy subgroups. That's a bigger class. And you can iterate the constructions in 1 and 2. Now, if you take a Levy subgroup of a Levy subgroup, that's a Levy subgroup in the original. So that doesn't give you anything new, but a pseudo-Levy subgroup of a pseudo-Levy subgroup, and also a Levy subgroup of a pseudo-Levy, though those are giving you genuinely new groups that don't fit in classes 1 and 2. And basically the theorem of Borel de Siebenthal together with, I forget what, tells you that if you iterate 1 and 2, you get everything. You get every equal rank subgroup. Now, there's also the question of conjugacy. That's actually a little tricky, but we handle that. And so you can compute, you can do this computation. So let's do this. Let's set G is equal to SL2. Let's do SP4. What should we do? Let's do GL3. Oops. Subgraph, I think. Nope. I forget the command. Subgraph. Okay, it's always a mistake to try and do these things on the fly. This is the graph, but that's not what I wanted. Okay, so here's what I'm going to do. Let's do more interesting. Let's say G is equal to GL4, or let's do 5. And let G be the subgraph. And I'm going to write this to a file. And then I'm going to process that file. So there you go. That's the partially ordered set of subgroups of GL5. And it's a little bit interesting. So let's see. So there's obviously from each entry, the torus is dropped. So the bottom is really the four-dimensional torus. A3 really means GL4 cross GL1, and so on. And so they're just various GLs, but the closure relations are maybe not quite so simple as you might think. These groups are parameterized by partitions, but it's not just the closure relation on partitions. It's kind of an interesting graph. And anyway, as you see, you can generate these very quickly using the software. So let's look at an interesting example here. So this is E7. So these are all equal rank subgroups of E7. And Levy subgroups are illustrated in red. Pseudo-Levy subgroups are in green. And the groups which are neither are black. So for example, E7 has a pseudo-Levy subgroup A1 plus D6. So notice this group is rank 7 and it doesn't have a torus in the center. So this is not a Levy subgroup. Similarly, A2 plus A5, A7, and so on. Now, there's a Levy subgroup of E7, which is E6 cross GL1. And anyway, you iterate this and you get this family. And almost all of the groups that you get are either levies or pseudo-levies, except for these three over here. Everything else is red or green. So if you look down here, there's kind of an interesting chain. There's A1, there's a Levy subgroup A1, there's a Levy subgroup 2A1, 3A1, 4A1. There is a subgroup 5A1, but it's not a levy, it's only a pseudo-levy. And there's also a 6A1 and a 7A1. And those are neither. Now, the fact that there's a 7A1, you can see because -1 is in the Weil group of E7. And according to Carter, -1 can be written as a product of 7 orthogonal reflections. And so that's giving you this 7 copies of A1. And it turns out it's not a pseudo-levy, which is sort of interesting.
Jeff, these things that you're, I mean, these pseudo-levy, aren't they like endoscopic groups?
Yes.
Group? Okay.
Yeah, they're I mean, strictly speaking, they're on the dual side. So
Yes, right.
you get endoscopic groups of G by taking the dual of a
Yes.
pseudo-levy of G check.
Okay.
Absolutely. Yep.
Jeff, I have a very elementary question.
Yes.
What are those semi-simple elements whose centralizers are not toric? Is it because they have a complex eigenvalues?
No, it's not that. But it's that. I mean, just for a simple example, take in. Whoops. Let me just write something here. In SP2N, take I sub k minus I sub k or R. Take diagonal I sub m I sub a minus I sub b I sub a minus I sub b. The centralizer is SP cross SP. And the way to think of them is that the way you get a maximal pseudo-levy is you remove one node from the extended Dinkin diagram. If you remove a node from the ordinary Dinkin diagram, you get a levy. But if you think in the extended Dinkin diagram, that's how you get these things. So for example, in type C, the extended Dinkin diagram has a double bond at each end. And if you remove a node in the middle, you get SP cross SP. Other questions? All right. Okay, here's another kind of question that comes up often. What are the conjugacy classes of the parabolic subgroups of a given group? So, this obviously comes up in studying representation theory. You use these for constructing representations by induction.
Do you mean conjugacy classes of Levy factors?
No, actual parabolics. Like Levy factors is a different question. So I was about to say that there's a closely related question about Levy factors. So for example, if you take a simple group, if any node of the Dinkin diagram gives you an SL2 Levy factor, and if the group is simply laced, those are all conjugate. But there are every node in the Dinkin diagram gives you a different parabolic. And I'm talking about the latter. So, so here's an example. Take all the real parabolics of the split form of, oh, I forgot to say, you take all the real parabolics of the split form of E6. Let's do that. Sharp all real parabolics of E6S. There are 64 of them, which is 2 to the 6th. And let's, I meant to put this on the slide, but I guess I forgot. So here are the 64 parabolics of the split form of E6. There's the split torus, and then there's an SL2 and a bunch of GL1s, and there's another and another and another. For each simple root, there's one of those. And then there's some SL3s and SL4s and SL5s and so on. And then right down here, there's a SO55 cross GL1. Actually, there are 2 of those. It's sort of interesting. And here there's an SO44 across 2 GL1s. I think there's only 1 of those, and so on. So what is this telling me? This is telling me the parabolics, and this is telling me the Lie algebra of this group is SO55 cross GL1. And it's telling me the group is disconnected. So one of the things that people often want to know is exactly what is that Levy factor? Actually, somebody just asked me this the other day, so I thought I'd do this example. Let's take this, this group, this Levy factor inside E6. On the Lie algebra, it's SO55 cross GL1, but what is it really? Often figuring out these isogenies and so on is tricky. Well, Atlas gives you lots of tools. So first of all, the components rank is 1, and that is to say the component group is 2 to the something. It's the number of Z2s, and there's 1. So that says that the order of the component group is 2. And here's the description of the center. Well, there's no circles in it. It has an R plus factor, and it has a Z2. So the center is R cross. So the group could be SO55 cross R cross, but it can't be because the center of that would be bigger. And you can also figure out the center of the semi-simple group. And so for example, the group could have been PSO55 cross R cross, but anyway, you put this information together and you conclude that this group is precisely SO55 cross R cross modulo plus or minus 1. So this is the kind of thing that's often people struggle to figure this out. And, you know, if you're constructing some Eisenstein series or something from this thing, it's important to know this because it affects the structure of the calculation. All right, that's an example. Here's another one. This was just kind of interesting. Take a complex group and a Cartan subgroup and the Weil group. Well, the Weil group is, we all know about that. It's the Weil group of the root system. But what if I give you a real group and a Cartan subgroup, and I ask you for the rational Weil group, which is to say I don't want to call it the real Weil group because that's a little confusing. The Weil group of the rational points. It's the normalizer of the torus. Oh, I'm sorry, I forgot to mod out by H of R here. And that's an interesting group, and it's not necessarily the Weil group of a root system, and it's an important thing to compute. So there's an algorithm for this given by Knapp and Vogin years ago, and we implemented it. So let's look at an example. Oops, where's my example? Oh no. Oh, I didn't put it in the slides. Okay, let's just do it here. Let's set G is equal to E6 F4. And let's set H is equal to the Cartan classes of G, the fundamental Cartan. And print real Weil of H. Oops, sorry, GH. Okay, so the group is F4, and it's the group whose maximal compact, sorry, excuse me, the group is E6, and the maximal compact subgroup is of type F4. And it tells me here that the real vol group, it's got this product decomposition, and it tells you the different pieces. Well, WC is type A2, A is trivial, and WIC is of type D4. So I'll just tell you what the answer is. It's W of A2, L times semi-direct, W of D4. So that's kind of interesting. W of A2 is S3. So it's S3 times D4. So D4, of course, has the marvelous triality, and S3 is the automorphism group of that Dinkin diagram. And the vol group I'm getting is this thing. But this is one of these things that I didn't understand when I first saw it, because by theory, the answer is the vol group of F4. This is the fundamental subgroup in a particular real form. I know that the answer is the vol group of F4. And so this proves theorem. The vol group of F4 is S3 semi-direct W of D4. I don't know if anybody else in the audience knew this fact. I was amazed by it. I didn't think the vol group of F4 could be understood in these terms, but there it is. Bert Costin knew this, but I'm not sure anybody else did. Anybody know this besides David? Good. Okay, so my next example is about nilpotent orbits. Take the set of nilpotent orbits in the Lie algebra. And I define CO to be the semi-simple part of the centralizer of an element of the orbit. This plays an important role in the theory, and it's important to understand it in some detail. The component group is known, and I put known in quotes because, well, for exceptional groups, it's just given by some tables. And here's an example. When G is E8, there's an orbit whose name is this thing, if you look it up in Carter's book, for example. And it tells you that the identity component is of type A3A1, which is to say SL2 cubed. And the component group is S3. So what we know from this information is that the centralizer fits in this exact sequence. And the question is, what group is it? Well, you can figure out in this case that, well, the action of the S3 on here is by permuting the factors. And in fact, the sequence splits, and the centralizer is of this form. Here is this is the table having to do with unipotent representations of E8. And each row in the table is a unipotent orbit. Whoops. This is the Dinkin diagram of a unipotent orbit. And some information, here's the type of the centralizer, the identity component of the centralizer. Here's something about the center of the derived group of the centralizer and some other information. And at the end of the line is a description of the centralizer. And I know this is kind of small, it's pretty hard to read this, but I just wanted to show you the table. And I want to pick out a particular line in the table here. So lines 50 and 51 are these two orbits for E8. The identity component of the centralizer is T1, that's a one-dimensional torus, GL1. And the component group is Z2. So what are the possibilities for the group? Well, it could be, of course, GL1 cross Z2. If the action is non-trivial, it could be GL1 semi-direct Z2. And something weird happened. I'm missing some slides. This is extremely disturbing. Give me a second. What happened?
Jeff, you can use the slides you sent me.
Yeah, that's what I was going to do. Give me 1 second. I don't know what I did. Let's see if that fixed it. Oh yeah, isn't that interesting? Yeah, I don't know what I did. Anyway, this was the missing slide from before. It's now there. And the ones that I said, Dima, that he's posted somewhere, this is on there, so that's good. And here's the one I was just doing. So the identity component of this group is GL1. So it fits in an exact sequence. C cross goes to the centralizer, goes to Z2. And this thing here, C2, so I should read this off. C naught, the identity component is GL1. This A naught is telling me the component group. C2 is telling me the number of conjugacy classes of involutions in this group. So if you think about it, that tells you that the action must be non-trivial. So it's by Z goes to Z inverse. And the sequence doesn't split because otherwise this number would be different. And so this is, and in fact, this group turns out to be the unique extension like this, which is not split, which is the Ve group of R. I didn't know that could happen. Now, the fact that it's the Ve group of R, I think, is misleading. I don't think that there's some deep significance to that. But it's interesting that you get this non-split extension. And as I said, one of the things we had to do was understand all of these, and that's one of the things that we did in the course of computing unimportant representations. And I think that's where I was going to stop. Oh no, sorry, one last thing. Well, maybe I'll skip the last thing. I'll just say what I was going to say, which is another thing people are interested in is branching to K. And here I've given an example of a representation of SP4. This is the spherical principal series of SP4 with infinitesimal character rho, and its restriction to K. And so you can see here, it has the trivial representation with highest weight 0 and dimension 1 is of multiplicity 1. And then there's some other representations, and then you get some higher multiplicities. And we can explicitly compute the K spectrum of any representation out to any given height. And that's something people might find interesting. And with that, I'll say thank you. I love the applause part of Zoom. That's great. Thank you. Questions?
I have a question. What about unipotent representations of classical groups? Are they known to be unitary?
That's a complicated question. So what's known is if you take literally a split classical group, by that I mean SP2N or SONN or SON plus 1N, then in Arthur's book is a proof that the unipotent representations, those unipotent representations are unitary. There's a description of those representations and the proof that they're unitary. If you take a closely related group like spin, it's quite possible you could prove this result, but it's not, it would take a little bit of work. And if you pass to a non-split group, well, I think quasi-split groups are done, the unitary groups UNN, but once you get away from split groups, I don't think anything is known in general.
Except for the compact form.
The compact, right.
I have a banal question. Is there anything about the p-adic?
Oh, did I think about p-adic? Is that the question?
Is there any computational tools for p-adic?
That's one of my favorite questions. I believe that there should be, that a lot of the tools that we've developed apply and to tell you a lot about p-adic groups. In particular, this sort of combinatorial stuff about epipelagic representations and such things. They're closely related to the kind of constructions we do. And so there should be, excuse me. So it would be great if there was such a tool, but it doesn't exist. Other questions?
I would, you more or less implied this, but the point is that Atlas can compute a lot of things about Weil groups and about semi-simple elements and their centralizers, nilpotent elements, and all these things have meaning in p-adic representation theory. There's no systematic tools for like the is unitary command, but nevertheless the software can help you do a lot of structural calculations that are relevant to p-adic representation theory.
May I ask if the software can compute Brouillard decompositions in classical groups?
Yeah, sure. That's one of the when you sorry, when you say Brouillard decomposition, what do you mean exactly? Just the whoops, I think you're muted.
Yes. So to write G as U, T, W, U prime for U and U prime unipotent, say to fix some Borel. T
that you Brouillard. So the short answer is no, in that we don't ever write down elements of the group except for semi-simple elements. So we don't really think about things like that, like if you're giving a decomposition for an element. So maybe that's the answer. David might have a slightly different answer. I don't know.
I mean, a lot of the software begins with understanding algebraic geometry questions about the Brouillard decomposition. But the question of, as Jeff says, taking a particular group element and finding its decomposition, that's not that's not done.
Right, but the combinatorics of it, the geometry of it is certainly there. I mean, we have the Weil group and things like that.
Thank you.
So, as far as I understand, unitarity is one of the main goals you set to yourself, but the software is in no way bounded to unitary representations, right?
Correct.
Right. Are there any further questions?
So I guess in some sense, all of this is pretty much extendable, right? I mean, you can add algorithms and just enhance the options of features.
Yes, absolutely. So, I mean, I did a little bit of typing. There's a scripting language for the software, and you can write scripts to do all sorts of things. In fact, there are tens of thousands of lines of these, and yes.
Any further questions?
For representations of Hacker algebras, is it similar or F1 Hacker algebras?
In principle, well, so we do have some Hecke algebra stuff built in because it comes up. I wouldn't say that we exactly, we think about general representations of Hecke algebras, but the technology is there, and you probably like this question about p-adic groups. I think the first step of that would be to implementing, certain representations of Hecke algebras. It's a lot closer to what we do, and so, it's not built in, but I think that's not far away.
And what are the limits actually? So E8 to do completely by Atlas is too difficult. E7 it works, and for classical groups.
So you're just wondering about how big a group we can do or something?
Yes.
Yeah. So, well, to give you an idea, to do some of these, the hardest thing, well, it depends what you want to do. So, for example, if you wanted just to list like the Langlands classification for a group, that's fairly easy, and you could probably do, SP of rank 12 or 13 or 14 or something. I'm not sure. Other calculations are harder. The most difficult, the most demanding calculation we do is the unitarity calculation. And for a couple of, the length of the calculation depends a lot on the representation. For the hardest examples in E8, I forget, it took us 36 hours or something on a machine with almost a terabyte of RAM. So that's kind of the limit. But typically E8, groups of rank 8 are beginning to push the edge of what we can do. But classical groups of rank 8 tend to be a little bit simpler. I don't think we've ever tried, but probably for the symplectic group, you'd run out of steam maybe around SP rank 10 or 12 or something.
Okay.
Maybe I can add that about a month ago, we managed to show the trivial representation of E7 was unitary purely using Atlas, which is the most difficult case on E7, and that's now doable. So I mean, it's even that's not trivial. That's the point. But now it's been done at a level where E7 and down is accomplishable.
Yeah. So Steve is telling you something which we find slightly embarrassing, which is that for us the discrete series representation is obviously unitary. And the hardest representation to prove unitarity are the smallest ones, because they have, the way we prove it is you write an irreducible representation as a linear combination, a formal linear combination of standard modules. And the smaller the representation, the more complicated that expression. So for us, the hardest representation to prove unitarity is the trivial representation.
You said that much better than I did. I'm sorry.
No, it's quite all right. Other questions?
All right, thank you very much again.
Thank you. Bye, everybody.
Next week, we have a talk by Dmitry Timoshev from Moscow State University on some geometric topics, real orbits in spherical homogeneous spaces. Hope to see you there in a week.